let's continue our discussion by comparing the free energy between these two cases. So the first case is actually the same as the one-dimensional case. So one domain free energy would be the energy term minus. It's a bit tricky part, but the thing is that you may consider this is natural, but why do we have this half factor? That's because for each spin, we have these 4 interactions, but each interaction is also provided by this spin as well. So it's kind of double summation. So it's just we divide it by half here, divided by 2. Yeah. And of course, the same entropy term is because this up spin or down spin. Yeah. And the tricky part would be here. And what is this mysterious omega term? I will show you. So this main case is first, the background interaction would be something like this. And we assume that I didn't explicitly put it here. This is a domain with the length n. So the domain length is n. This variable was not necessary for the one-dimensional case because it's always 2. But the domain length is n. So it's like, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 10, 11, 12, 13. So it's a 13 here. Yeah. Then, because this domain provides the positive energy, so it will provide 2J and this is factor 2 because without this domain, without domain, it was minus J, but with domain, it plus J. So difference is delta J is actually 2J. Yeah. And there's an entropy term. So entropy term is minus KBT and log. And the possibility or the total number of possibility of domain with the length is given by this one. But there is additional up-down symmetry because this can be down island in the sea of upspin or up island in the sea of downspin. So because of this up-down symmetry, it also has this extra 2 vector. Yeah. I didn't put. Yeah. This is a interface separating n spin. Yeah. Well, it can be different from domain length, but it's a similar. This boundary part doesn't actually separate the spin, but it's negligible. Yeah. So this part is actually for parallel spin, and this part is for anti-parallel spin. So the only non-trivial part and the hardest part for certain is to calculate this omega. this part. And one nice thing is that we don't need to actually exactly calculate this one. Certainly that is an interesting mathematical problem, but we don't actually need that. Because we only need to, our final destination would be just give some inequality rather than equality to estimate the critical temperature. So let's estimate the upper bound of omega. Why is the upper bound? Because we will estimate the number of such domain like this. So for example, let's just get this figure. And let's just draw this boundary of this. If you look at this boundary, suppose you start from suppose you start from here and walk from here by following the path here, like this. And you have to return to the original place, like this. So this path, the enclosing path, can be considered as a random walk of length n. Of course, I intentionally put it a blank part here, because this is not just a random walk, not just any random walk. Because suppose you are standing here, then in principle, you can walk from here to here, or here, here, or here. But to make a domain, at least a necessary condition, not sufficient condition, necessary condition would be you cannot go back to the original place where you come from. So you only have 3 possibilities at any time, except for the initial point, but that's ignored. That's a negligible. So this kind of random walk is called self-avoiding random walk. Self-avoiding random walk means that it's a random walk, randomly just from here to here, but you cannot just retrace your step. That is called a self-avoiding random walk. Of course. So this means that at each point here, there are 3 directions here. 3 different choices for each step. But as I already mentioned, this is necessary condition, not sufficient condition. Because even if you do that, it's completely possible that you have that walk, which is certainly more than 2 domain. It's a 3 domain then. This one. So this one actually grossly overestimate the number of such a domain. because every domain should satisfy this condition, but not all the work satisfying this condition can be a domain, a single domain. So if you follow this self-avoiding work with the length n, in principle, it's a very gross estimate, but three to the power of n interfaces, because there are always three possibilities for every branching point. But of course, this is gross overestimate, because many of these self-avoiding paths is not neither self-avoiding or nor closed. It even has a restriction that it should go back to this place. So it means that the of such an interface should be smaller than 3 to the power of n. But in fact, this only considers the length, right? So it has this one and this one and this one, even with the same length. So in fact, there should be extra factor n here. Still quite approximation, but times n different position for the center of mass of a given interface. Because this one can be here or here or here. So you have to consider all the possibility of the different location of the center of mass. So the upper bound, the real upper bound for this domain is given by n times 3 to the power of n. And there's lots of other such a approximation. Is that for object 2D, compact means neither is too large or too small, because this kind of domain, this typical domain, should be at the order of this n here, the line there, the linear dimension, should be proportional to the square root of number of spin here, for this domain to be a meaningful compact object in two-dimensional system. So two domains of the comparable size. This is also scaling argument. So a lot of estimation or the approximation is going on here. So in this case, finally, you can see that, so the difference between is given by 2jn. If you recall this difference, this one cancel out, and we have this term, and this one minus this one. So in this case, we have this ABT log omega n. The factor 2 was canceled out by this one and this one. Yeah. And because this omega has this inequality, and this log is the monotonically increasing function, and there's negative sign here. So it should have this ABT, and let's move this. log of n to the power of this one. Yeah. Because of this inequality here. And because of this one, we have extra, the kind of proportional thing similar to KBT log of n in this one. And by using the property of log, it's a square root of n KBT log n. Yeah. No, not this one. Have to be very careful about this. Let's just treat this later. Yeah. So in this case, if this particular quantity is larger than 0, then by this inequality, if this one is larger than 0, this one automatically become larger than 0. So this one become larger than 0. Or finally, there's a possibility that the ordered phase can be actually energetically favorable compared to the fragmented two-domain case. Then what is this inequality? Then let's just consider this inequality. So this inequality, well, let's put this one as well, square root of n. Yeah. Then this inequality, no, not this one. Should be uppercase. Sorry. Then this inequality, this one actually become KBT if be smaller than 2j over log 3 plus log n divided by square root of n. It's a simple rearrangement of terms. And in the thermodynamic limit, n goes to infinity, then of course this is a pretty simple argument that as I always emphasize, this polynomial is always stronger than log, and exponential is always stronger than polynomial. So it should be 0. So in this case, the condition become KBT should be smaller than this one. So in this case, this condition, I will just put it like this. KBT over J. This condition guarantee that ordered phase. Why is ordered phase? Because this condition automatically satisfy this one domain or the completely ordered phase, the left one, has a smaller free energy than the right one. So this case, this condition will make the system ordered. Ordered here means that F1 domain is smaller than F2 domain. But we know that if t goes to infinity, it must be disordered phase. And of course, if t is 0, it's ordered phase. And the tricky thing was, in one-dimensional system, every finite temperature belongs to the disordered phase. But for this two-dimensional system, clearly, if Tc clearly if kBt is smaller than this, this is over the ordered phase. So I will sketch this. Temperature goes to infinity and temperature goes to 0. We know that this is ordered phase, and this is disordered phase. But we know that there's a certain temperature, or 2J over kBt log 3. This one guarantee that for temperature less than this one, all of these should be ordered phase, like this. So this means that there must be some Tc here that will actually divide the ordered phase up to this point and disordered phase up from this point. So this formula actually sets the lower bound of Tc, which is this Tc should be at least greater than this value, which is 1.820. And we know that from the Onsaga solution, exact value of Tc is 2 kb. Let's see. It should be 2.2689 something. Well, not quite a close approximation, but still, we are correct about this estimation because the Tc is larger than this value. So this argument, because this inequality guarantees the ordered phase below this point, there must be some Tc above this level that distinguish between the ordered phase and the disordered phase. And so this is a very nice argument to actually prove that. And if you compare this one is a one-dimensional Ising model, the biggest difference is that here, in the one-dimensional case, this energy term is nothing to do with the system size, independent of the domain. But this entropic term increases with the system size. So it's always it's a kind of obvious that this entropic term dominates the entire system. But for two-dimensional system, this part, this energetic part, is also depending on system size. So there can be some subtle trade-off or some balance point between this energetic term and the entropy term. That will make this argument. So I think perhaps this is the most important takeaway from this two-dimensional Ising model, because the calculation itself is just too complicated. So we actually, even the textbook doesn't really care about this, but this critical the argument for the critical temperature, this is a very useful and nice exercise, I believe.